Okay, good afternoon, everyone. Okay, very happy to see you again for another course. Okay, so in this semester, I also guide all of you to study the course of Smart System in Automation. Actually, we need to change the name of course a little bit because I will instruct all of you about optimization methods for smart systems. But that's okay. So actually, for this course, we have some lab lessons, but I will cover the lab activities for this course. That means I will guide you to do the course project. Okay, instead of doing the lab lesson. Okay, so in this semester for this course you don't have lab activities. Okay, we have course project. Okay, yeah, and later on I will give you the details how to choose the roommate. Okay, how to choose the topics of the course project, and what is the maximum number for each group, blah blah. Okay, so for this course we have 12 classes for theory and more than 4 classes for course project. Okay, so totally we have 16 classes. Okay, yeah, to finish this course. And one more thing I would like to emphasize. Okay, this course is not easy to pass this course. Okay, so if you don't know uh, how to write the MATLAB code, okay, how to understand some optimization methods, okay, not easy to pass this course. Okay, it's different from the course of electric machine. Electric machines, if you do homework, okay, you attend my lectures, okay, you pass the lab lessons, okay, yeah, it's easy for you to pass the course of electric machine. But for this course, okay, even though you attend my class, okay, you need to do homework, you need to practice with the MATLAB code. Okay, yeah, I also send the announcement to all of you. You need to install the MATLAB software, and the version is 2024B. Okay, I also send email to all of you. And for this course, we have one TA, Đăng Tâm. Yeah, she will have all of you how to clearly understand my lectures, how to run the MATLAB code. Okay, and how to do the project. Okay, yeah. So okay, this week we have the online class, but next week we have offline. Okay, we have on-site class. Okay, next week I will come to the campus and give a lecture to you. Okay, so for now, for this is the middle of November. So some weeks we study more. Okay, so this week we only study one class, but for next week maybe we study 3 or 4 classes. Okay, try to finish this course earlier, and then you have more time to uh, prepare for your course projects. Okay, yeah. So now we go to the lecture 0. I will give you the introduction of this course. Okay, so I already uploaded some lectures into the video Moodle. Okay, so you can download them. For example, lecture 0, lecture 1, and I also upload some textbooks. Okay, for this course. Okay, please download it, and you can read the textbooks at home. And blah blah blah. Okay, and now we come to the lecture 0. Yeah, that means the introduction of this course. Okay, yeah. Okay, so first of all, you need to understand what is the concept of smart systems. Okay, yeah. So when we mention about the smart system, we normally think about a smart device, right? Yeah. So what are your systems? Okay. So we should have input and output. Okay. Every systems we have input signals, we have output signals. Okay. So this is system. So smart systems. So smart system including smart device. Okay, smart device. What else? Smart um, operation. Okay, and that means smart operation, smart decisions, blah blah blah. Okay, we have smart actuators, actuators, uh, and what else? Smart communication. Okay, and so on. Yeah. So for this course, we will skip smart device. Okay, because you already study another course in relation to smart device. This is sensors, right? Industrial sensors and actuators. Okay, so for that course, you understand we have some smart sensors, smart current sensors, smart voltage sensors. Yeah, smart humidity sensor, temperature sensor. Yeah, we study a lot of sensors. Okay, the smart sensor. So we will skip smart device. We also skip smart actuators because for the course of industrial sensor and actuators, you also study some intelligent actuator. So skip. We skip the smart communications because you study another course, for example, computer network or industrial networking, right? So next semester you study industrial networking. So always skip smart communication. So we focus on smart systems operation. Okay, what's in the smart operation? That means we have some optimization methods. Okay, to help us give the correct decision. Okay, yeah, to help us give the correct um, yeah operation. Okay, the correct procedure. Okay, to control the system. Yeah. Yeah. So to get the smart operation, you should study some optimization methods. Of course, we have many smart operation systems. For example, you study machine learning, right? Yeah. So later on, I will tell you. Okay, so look, the smart system are context-aware application, not built inside by incorporating IoT, data such sensors, device, media application, and open web. Okay, blah blah blah. Okay, but so we skip this. We skip because we just focus on the smart operation. Look here, smart systems to make the smart decision, okay, and control their environment by giving instruction or taking physical action through actuators. Okay, so how can we make the optimal solution, optimal decision? Okay, yeah. So we have many methods, for example, for machine learning, okay, predictable models, and so on. Okay, but for this course, we will use intelligence and optimization algorithms. Okay, yeah, we don't use machine learning to uh, to get this math operation. Okay, because you study another course. Okay, Professor Chung, okay, guide you the course of machine learning. Okay, so what is the difference between machine learning, right, and optimization methods? Very different. For machine learning, you should have the database. Yes, you should have as much as possible the database. Okay, so if you get more database, more correct database, you can apply into the machine learning models like CNN, like LSTM, like ANN, yeah, artificial neural network, blah blah blah. Okay, so we need the database, and we don't need any function, objective function. Okay, yeah. But for optimization methods, you must have objective function. Objective function. So what is the objective function? The objective function is the function to show the relationship between input and output. Okay, that means YE fx. Okay, objective function. So the function may be linear, maybe non-linear. Okay, it depends. It depends on the characteristics of application. Okay, but we know the output y is the function of input x. Okay, yeah. For example, if you would like to predict or forecast the weather, okay, predict the temperatures, forecast the temperature, okay, predict some price of the product, okay, predict the economy, blah blah blah. Okay, that means you need to use machine learning because you cannot make the function. For example, um, if you like someone, okay, for example, a boy, okay, like a girl, and he doesn't know the girls who will be accept his love or not. Okay, you cannot make the function because we don't know how to make the love function. Yes, that is true. Okay, what is the love function? This is the function of money, the function of the age, the function of for knowledge. Okay, academics, blah blah blah. No, okay, we cannot develop the love function. Okay, so if you cannot develop the love function, the objective function, okay, so you just predict, you just forecast, okay, whether she love him or not. Okay, so that means we should use machine learning. Okay, but for optimization methods, you must have the objective function. Okay, that means y is fx. Okay, so in summary, it depends on the application. Okay, so if we know clearly objective function, okay, we use optimization methods for my operation. So if you cannot develop, you cannot give the objective function, you should use machine learning. Okay, yeah. And if we have more time, we continue to study how to model and analyze non-linear systems. But this one, reverse years, we just finished the first learning outcomes. We don't have more time to discuss about neural network physics or neural physics systems. Okay, of course, we have a teamwork. Okay, we can get teamwork skills. Okay, cost level project management. Okay, and technical report. Okay, because you do the cost projects. Okay, so you need to write the report. Okay, you need to write the technical report. Okay, to present your result. Okay, to present what you have done in your project. Blah blah blah. Okay, yeah. So technical writing, or the technical reports is very important for you because you need to present. Okay, you need to make the report according to your result. Okay, so for learning activities, so you have homework for every lectures. You have student project. Okay, so for a maximums of 3 students. Okay, for each group. Okay, I just limit a maximum of students. So maybe one group has 1 student. That's okay. One group has 2 students. It's also okay. Okay, uh, the maximum is 3 students per group. Okay, but if you don't like to work with the other student, okay, you can work alone. Okay, but to be careful. Okay, the workload will be higher if you work alone for your project. Okay, so we have the final exams, 120 minutes. This is open book exam, but of course you have no internet access. You can use your laptop. Okay, and you need to install the MATLAB software 2024B. Okay, yeah. So today, okay, you should make sure you already installed the MATLAB software because the TA cannot help you to run the MATLAB. Okay. Um, yes. Any questions so far? Okay. So for no questions, next. Now assessment methods. Okay. Homework 20%. Yeah. We have the student project or course project with a presentation and a technical report, 50%. Okay, and final exam, 50%. For most of students cannot succeed with the final exam. Okay, because if you don't know how to write the code, okay, you don't understand the objective function I gave you, you cannot finish the final exam. Okay, you cannot do very well the final exams. So try to do homework, try to complete successfully your course project. Okay, and then you can pass this course. Okay, so if the results are incorrect, you get 0%. Okay, so if the results are correct but not good, that means less accuracy. Okay, so you get maybe half, 25%. Okay, so if the result is good and more accuracies, you get 50%. And remember that if you have no result, the results are incorrect. Okay, the results are failed, you get 0%, even though you have the presentation, you have the technical report. But if the result is wrong, you get 0%. If here you get 0%, that means 99% you fail this course, because if you don't know how to do course project, how can you complete very well final exam? Okay, so to be careful, you need to discuss with your roommate, you need to attend my class, okay, and you ask some support to TA, okay, and then she will give you some ideas, some suggestions how to do the course project. Okay, better. Remember that. Okay, so this is the rating policy. We convert Vietnamese rate and German rate. Outlines of the course. Okay, we study 9 lectures. Okay, so today we study lecture 1, right? Lecture 1, lecture 2, we study genetic algorithms. Lecture 3, evolutionary strategies algorithms, moth flame optimization algorithms, differential evolution, okay, BSO, ABC, cuckoo search algorithms, and the other one, the other methods, so the other optimization methods. Okay, so we hope we can finish 9 lectures within 12 classes, and then we have more than 4 classes for discussion about your course project. Okay, is it clear? Any questions? Okay, so software requirement, MATLAB software. See, in the 2020 version, but I suggest you to install 2024B. Okay, so maybe you need to upgrade your laptop performance. Okay, you upgrade your RAM, you upgrade your hard disk. Yeah. You do something. Try to install a MATLAB 2024B or at least 2024A. Okay, so if you don't like MATLAB, you can use Python, but for self-study. Okay, I will not teach you how to use Python. Okay, yeah, I will, of course I will teach you how to use MATLAB code, but for Python you study for yourself. Okay, yeah, because for machine learning you already learned Python. Okay, so yeah, finish the introduction of this course. Any questions so far? Any questions? So for I will check attendance. So for later on, Đăng Tam, please help me to check attendance. Okay, and if some students cut more than 4 classes, okay, they will fail the course immediately. Okay, and they cannot take the final exam. Okay, so every class, please check attendance. I will give you the list of students later. Okay, so for here I have okay. Here I have the list of the students. Okay, to choose this course. Okay, we have some students come from ECE 2020. Okay, some students 2021. Okay, yeah, and of course I will let you randomly choose your roommate. Okay, yeah, and then you need to inform me your roommate next week. Okay, remember maximum is 3. Okay, but maybe 2, maybe you walk along. Okay, it's up to you. Okay, so here we have some student for ECE 2021, 2022, and we have 2023. Okay, how many students? Okay, we have 28 students, and we have one exchange student. Okay, Jonah. Okay, early us. Okay, so yeah, you need to. I think you need to work with some local students. Okay, yeah. Mm, because I think um, okay, working alone is not good. Okay, yeah, I should try to make friends and do the project with some Vietnamese students, some local students. Okay, yeah, and later on I will send this list to her TA, and then she will check attendance. Okay, yeah. Any questions? Thế Bá, any questions?
No, I don't have.
Okay, so now we go to the lecture one. Okay. Okay. So lecture one is an introduction and the main concept of meta heuristics optimization. Okay. I mentioned before, to apply the optimization method, you should have the objective function. Okay. So the outlines of chapter one. Okay, the introduction. Yeah. Like classical optimization method. Okay, you study rate and descent methods. Okay, rate and computations and some examples in the MATLAB. Okay, so the lecture today will finish before 3:30 p.m. and then you have 30 minutes to hesitate about the code of lecture one. Okay, and maybe how to install MATLAB somewhere and so on. With heuristic methods. Okay, so what is the difference between exploitation and exploration? You know, yeah, exploitation and exploration. Probabilistic decision and selection. Okay, probabilistic decision, probabilistic selection. Okay, random search and simulated annealing. So here we have MATLAB code, MATLAB code, MATLAB code, and also homework. So we hope we can finish lecture one today. Okay, so, so sorry. So the main concept involves an optimization process. Okay. When you finish the lecture one, you understand how to classify the methods used for optimization problem solution, the main characteristics of evolutionary algorithms. Okay, what's the difference between exploration and exploitation? Okay, acception and probabilistic selection. Okay, yeah. So here are the main objectives of lecture one. Okay, now optimizations. What is the optimization? So optimization is the process of finding the best solution. Okay, to a problem among a big set of possible solutions. Okay, we have many solutions. We have many solutions, but what is the best solution? Okay, sometimes we say the best solution, sometimes we say optimal solution. Okay, optimal solution. And we should have the objective function like this. This is objective function. Okay, we okay, so any objective function. Okay, we have two cases. The first one is minimize fx. or we maximize fx. Okay, fx. Remember that this is bone phase x. Okay, bone phase. So this is the vector. Okay, this is the vector. If I use bone phase, it take me a long time. So I use the vectors. Okay, so x including how many elements? X1, x2, blah blah blah, to xd. Okay, xd. Okay, so that means we have d dimension, right? D dimension. Okay, for example, if we have x includes x1 and x2, so that means we have two dimension. Two dimension. What does this mean is a dimension? Okay, yeah, dimension. So dimensions that mean we have x and y. Okay, or we say here is x1, here is x2. Okay, we have we have how many element means how many dimension. So here we have d element, right? X1, x2, blah blah to xd. We have d element, so we have d dimension. We have two elements to the two dimensions. Okay, so it depends on uh, the application. Okay, we have more uh, more dimensions. Okay, so yeah, look, this is the vector. Okay, and we have the element, or we can say we have the decision variable. Okay, why? Because this is italic. This is italic. Italics mean variable, right? Variable. For example, if for example, here, look, we have the objective function. We have fx e x4 plus 5x3 plus 4x2 minus 4x plus 1. Okay, so here that means the vector x includes one element, so the dimension is 1. Okay, element. Yeah, so for this objective function we would like to figure out the minimum value of fx or the maximum value of fx. Okay, for example, we have the bank. Okay, so you send the money into the bank, maybe 1 million US dollars. Okay, and after 1 years, okay, you get how many interest, right? Interest, for example, for 7% of interest. So okay, so you try to maximize the profit, right? You try to maximize the interest when you send the money to the bank, right? Yeah, so that means we should have the objective function fx. Okay, yeah, or if we have the function like this, okay, what is it? This is a parabol, right? A parabolic function. Okay, so we would like to find the minimum, right? The minimum. For example, this is loss power loss, power loss. So we have power loss is the function of the current, right? In the function of the temperatures, in the function of frequency, something like this. Okay, yeah. So we would like to minimize power loss. Okay, so here this is the minimum. Okay, so this is the minimum values. Okay, this is the B lot function. Okay, so how many dimensions we have? 3. Okay, so x include current, temperatures, and frequencies. That means we have xe, x1, x2, and x3. Okay, x1 is for current, x2 is for temperatures, and x3 is for frequency. Okay, so we have the objective function, right? So B loss is the function of current, temperature, and frequency. And we would like to calculate, okay, what's a current, how many temperature, how many frequency in such a way that the P loss is minimized. Okay, yeah. For example, we have BCU. That means the copper power loss is I squared times R. Okay, this I is constant. Okay, so we just minimize I, right? So if we minimize, okay, we can minimize power loss, right? Okay, yeah. And then this is non-linear, non-linear, like this. Okay, so if here is the current, here is BCU, so this is linear, so the curve like this. Okay, non-linear, linear. Yeah. So the question is how many variable we need? How many variable? How many dimension? Three variable, three dimension, or one variable? One dimension. It depends. Okay, it depends on the objective function you develop. Okay. So if we come back to the uh, love function, love function. Okay, can we develop the love function? This is the function of what? The function of money, the function of age, the function of the family, family, family job, okay, and so on. Okay, so if you can develop the love function, you can apply optimization method, okay, to answer the question whether he or she love us. Okay, yeah, but no, this is real, not real application because yeah, we don't have a love function. Yeah, okay, so come back. So now you know what's in the objective function, right? Yeah, and here sometimes we need to minimize fx. Sometimes we need to maximize fx. It depends on the application. Okay, we should maximize the profit, right? You need to maximize the profits. You need to minimize the loss, okay, some power loss, some voltage loss, some yeah. If we have some negative issue, you need to minimize. If you have positive issue, you need to maximize. Okay, sure. But and then you can convert maximize to minimize or vice versa. For example, if we have mean fx, mean fx, that mean uh, you try to find the best solution to minimize fx. Okay, so if you time -1, okay, time fx, you get maximize. For example, here, right, we have this is fx, one dimension. This is minimize, right? This is minimize, right? Okay, so now if we have minus fx, okay, so become this one, right? So this is maximum. Okay, so if we find the best solution to minimize fs, and then you time -1, you get maximization. Or vice versa, if we have max, we find the best solution to maximize fx, and then you times -1. Okay, now maximization becomes minimization. Okay, yeah. Any questions? Any questions? But if we have the physical model, it's not easy to develop the objective function. Very difficult to develop the objective function. Okay, so for the cost project, I will give you the objective function. I will give you the objective function. I ask you to use some optimization method, okay, to minimize or maximize the objective function value. Okay, but your task, your task is to understand, try to understand the objective function I gave you. Okay, you don't need to develop objective function because it's cost project. Okay, I give you the objective function, and your responsibility is to understand clearly the objective function. Okay, how to apply some optimization methods to solve objective function. Okay, do you understand? Okay, good. Now we have another definition. This is lower and upper. Lower and upper. So variable, every variable, we need to set up lower boundary and upper boundary. For example, so if we have the curve, pH curve. Do you know pH curve? Magnetic densities and the magnetic intensity, right? So this is B or phi or S, phi, okay, sorry, no S. Okay, this is X, this is X, okay, as a proportional to I, proportional to electron is multiforce, okay? So we get the curve like this, okay? So when we increase current, that means we increase magnetic density. You also increase magnetic density, but after sometimes you get saturation. You get saturation. Okay, that means if you would like to operate magnetic circuits, we only consider this region. Okay, so for this region, we have the limitation. Okay, this is a limit. This is lower boundary, lower bound, right? Yeah, and this one is upper bound, upper bound. Okay, so we try to we try to operate in these regions. Yeah, because if higher than upper bound or lower than the lower bound, okay, it's not working. Okay, so every variables we need to limit lower and upper bound. Okay, bound. Any questions so far? Bound. Okay, upper bound, lower bound. Okay, so example. Look, we would like to minimize this function. Okay, we try to find the best solution to minimize fx. Okay, so how many dimension? Only one dimension. Okay, and they also give us the information of lower bound and upper bound. Okay, yeah, we find the minimum values of fx. Okay, in this limit of variable lower bound, higher bound. Okay, yeah. So how can you get the answers? How can you get the answers? Okay, so here, so we also find the solution of x. Okay, within this limitation -4 to 4. Okay, yeah. So here, look, x -4. Sorry, -4 to 1, not 4. -4 to 1. Okay, to 1. So now we have the limits of x. Okay, so that means we try to figure out what is x. Okay, okay, what is x in such a way that fx is minimum. Fx is minimum. Okay, and we know x is higher than equal to -4 and less than or equal to 1. This is -4. This is 1. Okay, so if you draw the curve of fx, you get this one, right? If you draw the curve of fx, you get this one. Now, problem. Okay, we would like to find the minimum values of fx, and then if you observe the waveform, we have 2 points. We have 2 points, point A and point B. You know, point A and point B. So remember, we hope we can get point A because this is the minimum point, not B. You know, of course, B at the minimum of this one, right? Of this region, but not the lowest point. The lowest point will be here. Okay, so if you don't have a good optimization methods, okay, you get trap. Okay, you get trap. That means you said point B is the minimum point, and then you are wrong. That means the result is incorrect, or you fail the project. Okay, actually, the minimum or the lowest point is A, not B. Okay, yeah, yeah. Okay, that's the example for the cost projects. Oh, so okay, so for the cost project, if you say point B is the lowest point, wrong. Okay, 0%. Okay, the minimum, the lowest point must be A. Okay, so that's the reason here we say multi-model. Multi-model. Why? Because we have the optimum here and optimum here. Okay, but we don't know. Okay, so we have some optimization methods will help you to determine point A. Okay, okay, yeah. So look, figure 1.1 here show the solution A and B, which corresponds to two different minima obtained from fx. Okay, so because we have two possible solutions, so we say multi-model, and the minimum represented by point A represent the optimal solution. Okay, so the optimal solution is what? E x, that is -3. So if x is -3, you get f fx mean, right? So if x here, if x is 0.4, this is minimum but not lowest point, you know. Okay, yeah. So how can we avoid the trap here? You know, you need to study another lectures. I will tell you how to avoid this trap. Any questions so far? I hope I get some questions from you. Okay, so no, yeah, okay. So from in general, the function fx could be non-linear. Yeah, non-linear. Because if we have fx, this is linear. Okay, you don't know. You don't know where is the max, where it mean. You know, because here come to minus infinite, and in reach come to positive infinite. Okay, so we don't know. We don't know if mean or max. Okay, so we hope you can get some non-linear function. Okay, like this. Okay, or like this. Okay, it depends, but we have a minimum. Okay, and this is maximum. Okay, otherwise we have no solution to determine minimum or maximum values of fx if we have non-linear, if we have linear function. Okay, so for in general, function fx could be non-linear with regard to its decision variable x. Okay, this is vector x, bond phase. This is vector x. So vector x has many dimensions. I mean, yeah, I discussed with you before. X1, x2, blah 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 to xd. Okay, we have d dimension. Yeah, and there are two kinds of algorithms used to solve the problems. Classical techniques. Okay, so lecture one is for classical techniques, and lecture two, three, four, five, blah blah. This is meta heuristic methods. Okay, yeah. So now uh, we have the comparisons between traditional scheme and meta heuristic methods. Okay, so for traditional methods, we use gradient. Okay, we use gradient of fx. Okay, to find the best solution. Okay, for example. Okay, for example, here we have the function like this. This is fx, right? So at the beginning, we have the point here. Okay, so you can figure out the tangent line of this point. Okay, so you get x-axis here. Okay, and then you draw another tangent point. You get here x1, here x2, yeah, and then you get a tangent point. You can get x3. Okay, and yeah, after some radian calculation, you can get a minimum. You can get minimum values of fx. That is the reason we say radiant of fx. You know, but radiant of fx is not good. Why? Because we have some limitation. Okay, I will mention to you here. Here, for example, we apply radian. Okay, we apply, I mean, the traditional method, radian. Okay, radian. We apply radian of fx to find the best solution. Okay, yeah, maybe minimize mean fx. Okay, so if we have the fx like this is fx. Okay, this one is x. Okay, so if we have the curve like this, very easy, at the beginning, if we apply radon means tension line, right? Tension line. Okay, for example, at the beginning we choose that point. This is xa. Okay, so we draw the tension line. Yes, you get here is xb. Okay, and then you get the tension line like this. Okay, and then here you get xc. Okay, so for xc you draw the tension line here. You can get xd, and xd here. Okay, you can get tension line. So this is the minimum. Okay, of fx. Okay, after 4 repeat xa, xp, xc, and xd. So xd is the best solution. Okay, but now we have another fx. Now we have another fx like this. Fx. Okay, so now we have fx like this. This is point 8. This is point B. Okay, and then you choose point A here, and then you draw the curve. Okay, you get this is xa, right? You draw the curve, you get here is xb, xb. Okay, and then you draw the curve here, you get xc, xc, and then continue. You get xd. Okay, and then here. Now you say the minimum of xx is here. You are wrong. Wrong. Because you get a trap. You get a trap. Okay. Actually, here should be here, right? So here is the disadvantage of radon. It's a disadvantage of radon because, okay, because you get trap. Okay, you conclude that B is in the minimum point, but not good. Actually, A is in the minimum point. Okay, so to avoid, to limit the disadvantage of radon, of radon, of fx, okay, they develop another method. Uh, this is meta heuristic methods. Okay, any questions? Xuân Quỳnh, any questions? Phương Anh, any questions? Female students?
I don't have any question.
Okay, so now for female Thế Bá, Bình, any questions? Okay, good. Okay, so no questions, continue. Now, look, if we use meta heuristics, we don't need, okay, don't require the functional information of the derivative in fx. Okay, that means they don't need to use gradient of fx. Gradient means derivative, yeah, we don't need to use, or we don't need to require the information of derivatives in fx. Okay, to perform a short strategy that minimize or maximize the objective function. Okay, but we need to set up the heuristic rules. Okay, we need to set up some rules. Okay, to find the best solution. Okay, for minimization or maximization of fx. Okay, yeah. Okay, now I hope you understand what the difference between traditional schemes and materialistic methods or optimization methods. Okay. Now we discuss radon descent methods. Radon descent methods. This is very traditional methods. Okay, it was developed. Okay, 1978. Okay, so we have some disadvantage. Sorry, we have some advantage. Despite its slow conversion, but the radon descent method is more frequently used for optimization of number functions because of its simplicity and easy implementation. Okay, we have simplicity and easy implementation, but of course, the disadvantage is slow conversion. Okay, so we start from initial bounds x0. So the candidate solution is modified iteratively during a number of iterations, so that may tentatively find the optimal solution. Okay, so let me explain to you. X0. Remember, this is the vector, right? So for the vectors, we have x1, x2, blah, 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 to xd. So for the first one, for the first iteration, x0 mean x1 0, x2 0, blah, 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 xd 0. Okay. So then we calculate x1 That means x1 1, x2 1, blah blah blah, x d 1. Okay, yeah, remember that. Yeah, of course you study digital signal processing, so we know, right? You know, right? Okay, so we have the general form. We have the general function how to generate the new solution based on the reverse solution. Okay, so K represent the current iteration and first symbolize the size of such steps. Okay, so fx is the objective function. So gfx represent the radian of the function fx. Okay, or sometimes we say xk plus 1 is xk minus alpha f fx over comma. Over comma mean the first derivatives. The first derivative. Okay. Yeah. So if you don't want to use fx over comma, you can use xk minus alpha g fx. G fx. Okay. Yeah. So case E the case E k order iteration, and k plus 1 mean k plus 1 order iteration. Okay. Iterations. So at the beginning, k is what? K0. You can guess x0. If k is 1, you can guess x1, right? Is x0 minus alpha g f x0. And then if k is 2, you can get x2 is x1, right? X1. What else? What else? X1 minus alpha g f x1. Okay, fx1. Or you can say x1 minus alpha f over comma x1. x1. Okay, so if we apply, if we apply the gradient descent methods like this, why we say descent? Because this is minus. This is minus in descent. So ascent, that means positive. Okay, but now we just use descent methods. Minus here. So if we use the gradient descent method, very simple. Yeah, you can get the minimum point after some iteration. After some iteration, but it's easy to get trapped. Okay, to get stuck. Okay. Example, I think. So we okay, and then so after we calculate x2 and x1, we don't know x1 better or x2 is better. You don't know. So it depends on your purpose. If you would like to find the minimum fx, so if fx2 less than fx1, so we conclude that x2 is better. The better one, right? Because we are looking for the minimum value of fx, and after we update x1 to become x2, and then we calculate fx2 and fx1. Okay, we recognize that fx2 is less than fx1, so fx2 is the better one. Okay, otherwise x1 is the better one. Okay, and then we continue to update. Okay, we continue to update ke3. We update x3 is x2 minus alpha f over comma fx2. Okay, and then we continue to compare fx2 and fx3. Okay, so if fx2 is less than fx3, that means your update solution is not good, because fx2 is also smaller than fx3. Okay, so it depends on we need the mean or max fx. Okay, we have the comparison, and then you can choose the optimal solution. Okay, yeah, here that's in this sentence, in the case of a minimization problem. In the case of the minimization problem, the descent direction can be obtained multiplied by -1, right? -1 here. Considering the opposite direction of g. Okay, so if fxk plus 1 less than fxk, which means the new generation, generation solution is the better one, is better than the previous one. Okay, any questions so far? Thế ba? Any questions? Uh, okay, no questions. Maybe I will ask someone. Okay. Đức Bình, Nguyễn Đức Bình, any questions? Okay. So yeah, I hope if all of you understand the lectures. Now come back. Okay, so yes, yes, this one. Okay, look. At the beginning, we are here. We are here, and this is the cost function. Cost is the function of what? Of weight. Of weight. So if we have minimum cost, okay, we are looking for the minimum cost. The minimum cost. So we apply radian. We apply radian. Okay, and after some times, okay, you make after some iteration, you can get what? The minimum cost. Yeah, and then you can get optimal solution. OTB. OTB mean optimal. Okay, so here is the minimum cost with the optimal weight. Okay, or if you don't want to choose initial point, here you can choose here. You can choose here the same, and then you try the radian. Yes, you get this one, right? Right, you get this one. Then here you can get this one. Okay, here you can get this one, and after some steps, okay, after some steps you can get minimum point here. Okay, yeah, so it's up to you. You can choose initial point will be here or initial point will be here. That's okay. Okay, so we yeah, we take a break 10 minutes. We will come back. We will come back at 2:30. Okay. So you have 10-minute break. And now teacher assistant will check your attendance. Okay. Tâm ơi, thầy sẽ gửi cái danh sách cho em ha. Sau đó em điểm danh cho thầy. Okay. Okay, I'm coming back. So, Tâm ơi, có nghe thầy nói rõ không Tâm? Okay, so yeah, we continue. Okay. So, yeah, we continue to discuss about gradient descent methods. But remember, now we have the gradient of a multi-dimensional function. Okay, so if we go back to this one, this is very easy because the solutions only has one dimension, x. Okay, but now we have many dimensions. Okay, for example, we go back to the example, we have B loss, E, the function of current, temperature, and frequency. Okay, so that means every solution has three dimensions, x1, x2, and x3. Okay, like this. You know, we have the objective function fx, and x has how many dimensions? D dimension. Okay, so we think about, we take the partial derivative. Okay, partial derivative here. So if we consider x1, we can get the gradient of fx with respect to x1. Okay, and then similarly we have to x2e the first derivative with respect to x2, and blah blah blah. We have gxd e the first derivative of f with respect to xd. Okay, so here we say partial derivative. Okay, yeah, so a little bit complicated because we have many dimension or multi-dimension. Okay, yeah. So look, um, for example, we have x equals x1, x2, blah 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 to xd. I so for more details, I have xe, x1, blah 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 to xi, and then blah 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 to xd. Of course, I a higher than 1 or less than or equal to d. Okay, we have xi. So I would like to update xi to becomes xi plus x. Okay, at the beginning we have xi. Now I update xi to become xi plus x. Okay, so when we update this one, so we get xi. Okay, xi, the new vector xi. So we take the gradient. Okay, the gradient. So the gradient change xi is the objective function values of xi, new xi, minus the objective function values of x. Okay, divided by x. Okay, yeah. And we continue, repeat and repeat for new vectors of x. Example. Now we have fx. How many dimensions do we have? 2. Okay, so every vector x, every solution x, we have x1 and x2. That means dA2 will have 2 dimensions. And then we need to set up the lower boundary and upper boundary. Okay, so x1 and x2 must be higher than or equal to -1 and less than or equal to 1. Okay, the question is what? The question is, please find the optimal solution. Okay, find the optimal solution x such that we get the minimization of fx. Okay, minimization of fx. So now we have fx e x1, fx1 and fx2 equal to 10 minus e to the power of blah blah blah. Okay, yeah. So we try to minimize fx by finding the optimal solution. Okay, so how can we do? Yeah, and if you draw the wafer, if you draw the curve, of fx, you get here. Okay, here is the minimum. Okay, yeah. So and then yeah, we can find x1 and x2. Okay, so we are very lucky because this function is unimodal. What does it mean unimodal? Because we only have one minimum point. Okay, we only have one minimum point here, so we say unimodal. So if we have this one, okay, to be careful because we have two minima, this is multimodal. Okay, so how can you get the answers? How can you get the answers? So now we follow the procedure. This is the general procedures of gradient descent methods. Okay, yeah. Step 1. The procedure starts selecting randomly a candidate solution xk, k is 0. So first of all, we determine x0 and we know x is what? X is x1 and x2, right? 2 dimension. So at the beginning, maybe we say x0 is 0, 0. That's okay. That means we assume x1 is 0 and x2 is 0. Okay. So at the beginning, you can random select, right? You can random select a candidate of xk. Of course, when we random select, but you should remember we have the boundary, x1 and x2 should be higher than or equal to 1 and less than or equal to higher than or equal to -1 and less than or equal to 1. Okay, we cannot choose any values outside of this interval. No. Okay, so the reasons is what? The reason is we already the boundaries, okay, to be set up before. Okay, so number 2, we calculate the gradient of gx1 and gx2. Okay, so gx1 is the first derivative of x with respect to x1, and gx2 is the first derivative of x with respect to x2. Okay, yeah. Because fx wanted to involve to decision variable. Okay, so the new solution can be built. Consider each variable separately. Okay, now the new solution. The new solution is here. Yeah, that means we only update x1. Okay, so x0 is what? X0 is 0, 0. Now x1. So for x1, maybe we only update x1. Okay, maybe 1, 0. Okay, yeah. So how can we update x1? How can we update x1? Yeah, we know x1 is x1k plus 1 is x1k minus n for gx1. So it is random for us to choose alpha. But remember, alpha is normally alpha is higher than 0 and less than or equal to 1. After that, we update x2. Okay, we update x2. Okay, so first of all, we update x1. Okay, and the second one, we update x2. Remember, x here mean element, element of vector x. Okay, so when we update x1 and x2, okay, we can get x1 vector x1. Sorry, here maybe not zero, maybe 0.5, something like that. Okay, so now we update the new solution. Okay, so this one we update what? This one we update element. But now when we update all element, you can get the new solution. Okay, so this process is repeated, okay, iteratively until a maximum number of iterations have been reached. Okay, so yeah, we just repeat. Okay, in such a way that you get the maximum number of iterations, and then we can stop. Okay, now, okay, at the beginning we are here. Okay, update, and then you can get here minimum point. Okay, now we have the pseudocode. Okay, here you need to understand this one here. So at the beginning we set up k to be 0. That means the first iteration. K, what is k? K is the other number of iteration. Okay, so we randomly set up, x1 random between -1 and 1, random between -1 and 1, and then we use y for loop. Okay, we use y loop. Okay, and then we set up what? We set up the maximum. We set up the maximum number of iteration, right? Okay, and then we calculate gx1. When we calculate gx1, we have x1 k plus x. Okay. Yeah. And when we calculate gx2, we only update x2 element. Okay, x2 k plus x. Okay, we keep x1 because this is partial derivatives. Okay, partial derivatives. Right? Do you agree with me? F what? We have a Taylor, right? We have Taylor's series. So we have f x over comma e fx plus delta x, right? Minus fx divided by delta x. Do you remember this one? This is the formula from Taylor series. So f over comma xe fx plus delta x minus fx divided by delta x. So now look, we have two variables. Okay, so when we update x1, we keep x2. When we update x2, we keep x1. Okay, and then after you get to x1 and to x2, we can apply the general formulas of rate and descent methods. We can update x1, we can update x2. Okay, so that means now we have vector x for after the first iteration is x1 k plus 1 and x2 k plus 1. Okay, yeah, and then repeat. Okay, yeah, you can guess vector x after second iteration, vector x after third iteration, blah blah blah. Okay, so if we apply this pseudocode, okay, into the MATLAB software, okay, yeah, you can get the result. Okay, you can get the result like this. Okay, here now you have 10 minutes. Okay, try to use MATLAB software. Okay, and you copy this code into the MATLAB. Okay, to run it. Okay, you can understand what is the region descent methods. Okay, yeah. Okay, now you just copy here. I open MATLAB. Okay, the MATLAB, and then you go to new strip. Okay, new strip. After that, you copy the code. Okay, just copy it. Okay, into here. Then here, copy it. Here, then here, then here. Okay, here. So I will explain to you. So over here we just delete. Okay. So from delete this one, we don't need this one. We don't need this one. Okay. So for save it, maybe I save here. This a lecture one, code one, lecture one. Okay. Yes. So this is the objective function, right? Yeah, this is, sorry, maybe I zoom. Yeah, okay. So this is an objective function, right? We use this is the format to set up the objective function to let the MATLAB understand the objective function. 10 minus e to the power of minus 1 times x to the power of 2 plus 3 times y to the power of 2. Here. Here. Where is 6? Where is 6? Let me see. Where is it? Here. Here, right? Here. Look. 10 minus e to the power of blah, blah, blah. Okay. Yeah. So, yeah, we should use this format. And then f, this is the function. Okay. F is the function. F is vectorized in line function strings. Okay. That means this is string and we convert string to become the function and the range, range minus 1, 1 and minus 1, 1. Why? Because we need to make sure x1 and x2 should be what? Should be higher than minus 1, right? Higher than or equal minus 1 and less than or equal 1. Okay? And then you draw the waveform. I mean, we draw this curve, this one. Okay? So yeah, you just remember some okay, we set up the number of deviations. Okay, 50. Okay, so dx is range 2 minus range 1 over blah blah blah. So how can we understand the code? Okay, this is range. Okay, this is the vector. That means range, this is a vector, right? This is a vector. So you get again range 1e minus 1, right? This is element, the first one, the second, the first element, the second element, the third element, and the last element. Okay. Yes. Yeah. Okay, so okay. So yeah, we have dx and we have dy. So you can draw the function of you can draw the objective function, right? The objective function. Okay. Then now we define the maximum the maximum number of iteration. Okay, at the beginning k0, and the maximum iteration is, you should use the percent, okay, to make sure this is the not. Okay, so the maximum number of iteration is 200. Okay, and each step is 0.001. Okay, each step is here, here, right? Each step. Okay, of course, we, okay, normally, okay, XE 0.001 or 0.0001. Okay, and alpha. Okay, we choose alpha is 0.05. Okay, so we can choose randomly x1 and x2. Okay, at the beginning, right? Now initial point selection. Okay, x range is range 2 minus range 1. Range 2 is what? Is 1. Range 1 is minus 1. So that's mean here you can guess x range is 2. Okay, and similarly y range is 2 because range 4 minus range 3. Range 4 how many? Range 4 is 1. Range 3 is minus 1. 1 minus of minus 1, you can get 2. Okay, and then we apply this format. Okay, this format is very important. Okay, so we randomly choose x1. Okay, this is range. What does this mean, range? Range mean random. Okay, so here you can type have range. Okay, and they will tell you what is x. Okay, what is x? Yeah. So range is the uniformly distributed pseudo-random number. Okay, between what? Between 0 and 1. Okay, on the upper interval 0 and 1. Okay, so if we say range, okay, maybe it's 0.8 and range 0.9. Okay, this is random number in the interval of 0 and 1. Okay, so yeah, and then we use y lob. Okay, so first of all, we calculate here we calculate z of x0, right? Okay, at the beginning, right? And then we update x1, we update x2, we update x1 to become vx1, we update x2 to become vx2, and then you replace into this formula, right? When we update x1, we use vx1, right? And we keep x2 like this. Okay, when we update x1, we keep x2. When we update x2, we keep x1. Okay, so here, and then when we update vx2 and we calculate gx2, so gx2 is x1 vx2. Okay, then we after you get gx1, we need to update the new solution. This is the new element. Okay, so right here we update the new element. Okay, we update the new element x1, we update the new element x2. Okay, but now we update of the new solution. That means, okay, so x1 new is x1 out, x1 out here, x1 out here. Okay, initial position. So x1 new is x1 out minus alpha times gx1, right? Look, x1 new is x1 out minus alpha times gx1. Okay, so Yeah, we update. Yeah. Then save it, run it. Okay. Okay. And then you can see, here, yeah, after some iteration, how many iteration? 200. You can get the optimal solution here. Okay. Yeah. Yeah. Yes. That means this one, yeah, and this one, I mean to this objective function, okay, get the minimum if x1 and x2 are on 0. If x1 is 0, x2 is 0, you get e to the power of 0, 1. So 10 minus 1, you get 9. So fx must be 9. Okay, so you can say fx. Okay, fx mean zn. Okay, zn is the value, right? Zn is the value of objective function. Okay, so now you can see the workspace. Okay, and you can see zn how many? Zn is 9. Okay, yeah. So I can type here. So we can use print. Okay, yeah, print. Okay, I forgot the format. Maybe I will type here have print of. Okay, F print. Okay, just print. For a long time I don't use, so I forgot. Okay. Maybe we use F here. Okay, we have the format. Okay. Anyway, I forgot. Maybe it's next class. Okay, I will remember. I mean, we can indicate. We can indicate the values Zn, okay, or you can use ChatGPT, okay, to analyze this code for you. Okay, so now this is the 3D curve. Okay, 2D, the 3D curve, and you get the minimum here. Okay, so at the minimum values of fx, that's in 9, right? 9. Why? Because x1 is 0, x2 is 0. So e to the power of 0 is 1, 10 minus 1 is 9. So now when you check Zn, okay, you get 9. How about the optimal solution? Here, the optimal solution is e, x1, and x2. Okay, so after 200 iteration, x1 is x here. Yeah, you can see x1 is 5 minus 5 to the power of e to the power of minus 4, so nearly 0, and this one nearly 0. Okay, so we finish. Okay, so now we apply the gradient and descent methods. Okay, yeah. For the solution with 2 dimension, here we have 2 dimension. How about 3 dimension? How about 4 dimension? Okay, so you need to think about it. So if we have the fx, okay, so if we have the fx, okay, with more dimension, for example, we have x1, x2, x3, okay, so blah blah. How can we write the code of gradient descent methods? Okay, or 4 dimension, 5 dimension. Okay, it depends on the application. We have the solution has many dimensions. Okay, So far, any questions? So if you don't understand the code, okay, later on, TAs will have you when I finish the lectures at 3:30 p.m. Okay. So for how many students already installed MATLAB 2024B? Okay, just type the message uh, into this message chat and I can know. Okay, how many students already installed MATLAB 2024B? Okay. Okay, so yeah, you should make sure, okay, next class you already installed MATLAB 2024B. Otherwise, yeah, as I mentioned before, for not easy to pass this course if you don't practice how to use MATLAB code. Okay, so you can use your ChatGPT or another AI platform to analyze the code for you. Okay, yeah, okay. Um, Okay, yeah, 2025. That's okay. Good. That's good. That's good. Okay. Yeah, I also use 2025. Okay. So yes. Yeah, just is an example of region descent method. Now we go to the next session. Okay, 1.3. Okay, we discuss about meta heuristics methods. Okay, that means um, we try to use another version of redundant methods. Okay, or we develop a new optimization methods. Okay, yeah. Okay, so yeah, we have some modification of radon-based methods. Okay, for example, the 2008, we have many of methods with multimodal behavior. Multimodal behavior means the function has several minima. So, if we use radiant-based methods, okay, maybe it would converge to a local minimum. Okay, we don't need local minimum, we need global, global minimum. Okay, I try to avoid local minimum. Yeah. Okay, so here for this one, we have multi-model. Yeah, look, we have some maximum, okay, but this one is local maximum. Here is, here the highest point, so we say global maximum. Yeah. For these figures is not differentiable. Okay, it's not differentiable. So that means we cannot perform the derivative, okay, or very difficult to use radiant descent methods with this one, okay, because we cannot apply radiant methods very well, because yeah, it is not differentiable. But for this one, that's okay. It's okay. Okay. Yeah. So if we use meta-heuristic methods, we don't need functional information of derivative. So that means meta-heuristic methods can apply for this function. Okay. Yeah. Okay, to generate is a strategy that minimize or maximize a particular objective function. Okay. So how can we avoid the information of the derivative? You can use heuristic rule. Okay, every optimization methods we have different heuristic rules. Later on, I will tell you. So, okay, maybe in some next lectures we mention about heuristic rules. Heuristic rules based on the simulation of different natural and social process. Okay, so we have different methods. Okay, to copy the behaviors of animals, behaviors, the social behaviors, so on. Okay. Yes. So this concept that meta-heuristic schemes usually consist of a population of candidate solution to optimize a particular problem. So we have the population of the candidate. How many candidate solutions we have? A lot. Okay. You remember every solution we have d dimension. Okay. So if we have solution 1, x1, we have x1 1 to x1d. So if we have solution 2, we have x2 1 blah 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 to x2d. Okay, the first subscript mean the order of solution. The second subscript mean the order of dimension. Okay, so if we have xk, we have xk1 blah 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 skd, you know. So here the combination of all, we say population. Yeah, we say population. Population. Yeah. Or we can say a population has many candidate solutions. Okay, here we just mentioned the candidate solution, not optimal solution, you know, just the candidate. Okay. Yeah. Okay. Yeah. So if we have more candidate solution, we have more opportunity to get the optimal solution, the best solution. Okay. Yeah. Then each of these candidate solutions behave as a search agent that leads the search strategy. Okay. For example, we have the objective function here, you know, and we have many ants. Here is sugar. And we have many ants. We have the population of ants. Okay, and 1 and 2 and 3 and 4 and 5. You know, we have many ants. Okay, yeah, and this is the sugar. And then when we start, okay, many ants will come, okay, to find the food, to find this sugar. Okay, so and then after some time, okay, so if the ant move, they will release one chemical, okay, to in such a way that the other ant will follow, okay, the reverse end. Okay, so if the ant come to the sugar, okay, so they will release more chemical, and then the other will smell, will get the information from this ant, and then many ant, okay, will come to here, okay, yeah, to take a sugar. That means every candidate, okay, every candidate solution behaves a search agent that leads to search strategy. Okay, yeah. For example, in our class, we have one student who knows these exam questions. Okay, and then he or she will tell to the other student, oh, I have the exams question paper, so we have the sample of exam question. Okay, please share to our other student, and then we work together, blah blah blah, try to get the concept of exam questions this semester. Okay, is it good? We have the search strategies. Okay, so the purpose is what to mark this course. Okay, yeah, so this is search strategies. Okay, so continue. Yeah, we have many with the heuristics methods. Okay, for example, we have traditional methods. Okay, traditional meta heuristics methods, random search, simulated annealing. When we have the new one, GIES, MFO, DEBHO, ABC's Google search, and so on. Okay, so now we are in chapter 1. Okay. Yeah. So meta heuristics is used to describe the general family of heuristics algorithms. Okay. Yeah, because we have many heuristic rule. Okay, rules corresponding to different methods. Okay. Yeah. Any questions so far? This is rule. Okay. Example. Yeah, example. Look, we have the objective function, right? We have the objective function. Maybe we figure out the minimization or maximization. It depends. Okay, but now we have fx, and every solution we have the dimension. Okay, yeah. So and then we need to set the possible candidate solution. Okay, so we have solution x1, solution x2, blah blah blah, solution xn. Okay, so the combination of x1 to blah to xn, you have n solution population, right? Yeah. So how many population we set up? It depends, more population. Okay, you can get the optimal solution. Okay, you can avoid the trap, you can avoid the stock. But if we have less population, maybe you get trap, you get stuck at the local minimum, local optimum, maximum. Okay, it depends. Okay, so sometimes we increase the size of a population. Okay, sometimes we decrease the size of population. Okay, it depends on the experience. Okay, so the meta-heuristics algorithms maintains a single solution xk, or a population of n, right? The population of n candidate solution. Okay, so this is the population. with n solution. N solution. To be careful, every solution will have d dimension. Every solution will have d element, and every pollution, every population will have n solution. N solution. Yeah. Or you can write here x1 k e x11 k x12 k blah 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 x1 d k. We have d dimension for the solution 1 and solution 2, yeah, solution 3. Okay, so if I use the vectors, that means I imply the solution, not element. Okay, element normally we use italic. Yeah. After that, we set up what? We set up a lower boundary and upper boundary. Okay, we also determine the maximum number of iteration. Yeah, the maximum number of iteration. Yeah, we don't know what's in the maximum number of iteration. Okay, so we randomly choose and then you run the methods. Okay, if you get the best solution, that's okay. So if you cannot get the best solution, you increase the number of iteration or decrease the number of iterations. Okay. So yes, okay. So when we update, okay. So now we have okay. So we have population. Population has x1, x2, blah 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 to xn solution. Okay, I just pick up one. For example, now we have BE x1, x2, solution blah blah to xi, and then blah 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 to xn. Okay, xn. So I just pick up randomly one solution of the population. Okay, again, a population has n solution, right? So I just pick up one. I just pick up one. Okay, I just pick up one. Yeah, so I just pick up one to evaluate the objective function. Okay, so if I randomly pick up xi, so you can calculate xi, right? Because we know x, we know objective function. So if we know xi, we can calculate the value of function with xi. Okay, so if fxi e, I choose minimize. Okay, so if fxi is less than fx1, okay, so xi is better than x1, or less than fx2, so xi is better than x2. Okay, yeah, so we can pick up, okay, solution by solution, and then we calculate the objective function value of fxik. Okay, so if fxik is the minimum value, that means the value of fxik is the lowest one. So xik will becomes the optimal solution. Okay. Yeah, and the value of objective function, sometimes we say the fixed value. Okay. This is the objective function. So you can get the fixed value of xi, right? Or the fixed or the objective function value. It depends. Okay. Sometimes we say objective function value. Sometimes we just say it's a fixed value. Yeah, everybody understands. Okay. When you follow this course, you understand. Okay. So if we figure out, in summary, if we figure out the minimization of fx, okay, and you recognize as fxi is the lowest one, fxi is the lowest one, that means xi is the best solution, is the optimal solution. Okay, yeah. And so here, at the beginning, we randomly set up the population. Okay, randomly set up the population. Okay, that means B K x1 case x2 case blah 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 xi k blah 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 xn k, they are on a vector, they are on solution. Okay, solution. And then we update the revert population to become the new population. New population. Wait, what does this mean, the new population? For example, so if I update x1 to become x1k plus 1, I update x2 to becomes x2k plus 1, blah blah blah. Okay, so you can we can get the new population, right? We can get the new population k plus 1. For example, you have your parent, okay, your fathers and your mother. This is the first generation, right? The first generation. How many solution? 2. So okay, so and then we can get your, okay, you here, okay, and your sibling, maybe your siblings, okay, two brother and two sister, okay, and this is the second generation. Okay, so the first population, okay, we have 2. So the new generation we have 5. 1 2 3 4 5. Okay, but desired population is only 2. So that means you need to eliminate. Maybe this one is not good. Eliminate. So, and this girl is not good, and this one is not good. Okay, so your parents will think about they give more money to you or to your sister. So the next generation we only have 2. The size is 2. Okay, and then continue, you get married, and then you get okay, the 2 kids. Okay, and now here they also get the 2 kids. Okay, so you and your sister think about, okay, the next generation, the third generation. Okay, we need to choose 2 or 4, okay, to follow, to keep the money from their grandparent. Okay, so maybe I delete this one, and then for the new generation I keep this one, this boy and this girl. Okay, yeah, so every population, okay, every generation, the number of solution must be fixed. Okay, the number of solutions must be fixed. For example, here, how many? We have n solution. Okay, so when we update from the population to the new population, you will also get n solution. Okay, n solution. Yeah, and then you will need to check whether we get the maximum iteration or not. Okay, if not, come back and then update the population, calculate and double check this condition is satisfied or not, and then repeat. Okay, after we get the maximum iteration, you get the best solution. Okay, yeah. Okay, I think we stop now. Okay, and then we have 30 minutes. Okay, to install the MATLAB. Okay, try to run the MATLAB code here. Okay, yeah. Okay, try to run the MATLAB code here, and then you need to submit your quick text. Okay, and you try to apply this rate and descent methods to Okay, to to answer question 1.4. Okay, look, 1.4 modify the program 1.1 so that it solve the following minimization brush. Minimization brush. Now they give us fx, right? Fx, okay. Fx, how many dimension of solution? 2, x1 and x2. Okay, we set up lower boundary, higher boundary. Okay, then analyze the performance of random descent methods, considering that the parameter n for assumes 0.05, n for 0.1, and n for 0.5. Okay, so you have 30 minutes. Okay, try to understand the MATLAB course and answer these questions, and you need to submit. Okay, you need to submit your homework. um, no, you need to submit your quiz text. Okay, okay, for maybe 4:10 p.m. Okay, 4:10 p.m. and you need to submit into the VGU Moodle. Here we have VGU Moodle. I will set up the quick test today, and you have 30 minutes or 40 minutes. Okay, submit the quick text here. Okay, try to apply the MATLAB course I explained to you before to find the best solution. To find the best solution in such a way that this function get minimum. Okay, yeah, do you understand? Any questions? Okay, now quick text 30 or 40 minutes, and please remember you need to submit on times 4 and 10. And now TAs will help you. Okay, good luck. Goodbye. Any questions? Do you have any questions? Okay, so if you have no questions, I will set up the quick test. Okay, quick test today. Okay. Yes. Hey. Anyway, I will set up the quick text. Okay, now you have 30 minutes to answer these questions. Okay, based on the MATLAB course I explained to you before. Okay, good luck and see you next week. Thế là Đăng Tâm sẽ hướng dẫn các bạn, hướng dẫn các em chạy code hồi nãy ha, và giải cái bài tập Prof 1.4 đến 4 giờ 10 thì mình nghỉ. Ok, bye bye.